Hi, this is Lou Prestia from EFI. In today's video, I want to talk about the relationship between tone adjustments of printed output and the way the color appears. Very often, quality problems with printed images relate to the color appearance of the print. When I'm trying to match the color on a print from an original scene or from some supplied copy, there's a tendency to go and make color adjustments as soon as I see a color problem. The reality is that color problems with the reproduction are most commonly rooted in tone. They're most commonly rooted in the contrast or the placement of the tonal values within the reproduction. So that when I make a tone adjustment, I actually correct color as well. It's a much more efficient way to correct color, and it's in fact much more natural since it's the way that the photographic process has historically worked. It's a little bit hard to understand, though, how it could be that when I adjust tonality, colors in my reproduction will change. So that's what we're going to explore in a little bit of detail. In order for you to understand this, we need to have a little background discussion first about what is RGB color, or red, green, and blue, what is this CMYK color that we print with, and what is the relationship between those two. Then I want to talk specifically about saturated colors. We're going to talk about saturated colors in terms of CMYK, and I'll give you a very easy and useful definition of a saturated color that will contribute to your understanding of how correcting tone ultimately can correct color as well. We'll move on to a discussion of tone curves so that we understand what the different tone ranges are and what a tone adjustment on a tone curve in a program like Adobe Photoshop or like the image viewer application that's part of the Fiery Graphic Arts Package Premium Edition can do. And then finally, we'll bring together all this knowledge so that you can gain an understanding and see some ideas about why a tone adjustment will shift color. When we talk about RGB color or additive color, we talk about colors that add up to make white. So the RGB model is sometimes called the additive color model. This goes back to the grammar school experiment you might remember, where we have 3 flashlights and we go in a dark room. We have a red, a blue, and a green light. And we can learn something about how colors interact by mixing those colors together. So you see at the left of this slide, when I mix the red and the blue light, I make the color we call magenta. Various other colors are made that way. But what's important to understand is that where all of those lights combine in the center as I show it on this slide, I make white light. That tells me that the white light that's all around me in the real world is basically composed of equal amounts of red and green and blue. We could get a lot more scientific in our understanding, but there's really no reason to do that. Our eyes measure red and green and blue colors. Essentially, the white light around us in the world is composed of equal or nearly equal red and green and blue components, which is why the light looks white to us. So when we talk about CMYK, the printing colors, the first question is, if our eyes measure RGB, why don't we print with RGB? And the answer is that objects in the real world that might be red or green or blue or some other color are typically opaque. So when I look at a red fire truck, the fire truck is red because its paint is absorbing 2/3 of the visible spectrum, that is all the greens and all the blues, and it's reflecting approximately 1/3 of the spectrum, the reds. That fire truck is opaque, so if I tried to print with red and blue colors together, for instance, and I printed the blue on top of red maybe to make some sort of a purple, the only color we'd see on the final reproduction would be blue. Since that blue ink on top of the red would be opaque, would be reflecting the blue and absorbing red and green as we'd expect, but would also be hiding that red ink that might be underneath it. When we print, and similarly in the conventional photographic processes, the emulsions we used were the colors cyan, magenta, and yellow. These colors selectively block portions of the visible spectrum, so that if I want to print a color like a blue, I'm not going to use a blue ink. I don't have one. I have cyan, magenta, and yellow. I'm going to use 2 colors, principally, that will block the 2/3 of the spectrum I don't want the eye to see. So the first color I'll talk about is cyan. When I print cyan, and I have a light, again a white light that is essentially red and green and blue in its components, cyan will block the red light. So the red light is filtered or absorbed by this cyan ink or emulsion that is in fact transparent. Green light is blocked by magenta. Notice that the green light is transmitted by the cyan. So each of our printing colors we can say has 3 characteristics about whether it absorbs or blocks, or whether it transmits or lets pass a color. Cyan ink blocks red, transmits green, and transmits blue. You can see that from the green light going through the cyan ink. Magenta ink blocks green. It transmits red, which you can't see in this slide since the red's already been blocked by the cyan. It also transmits blue. When the blue light comes through the magenta and cyan transparent inks, it actually bounces off the substrate and back to your eye so that it appears that we printed blue. What we printed was we printed the colors to filter out the red and the green. In this example, we didn't print any yellow. Yellow is the color that blocks blue, and a natural blue color would probably have some yellow in it in a real reproduction where the blue areas would not have any detail. They'd look like big blobs rather than actual blue objects. But in general, this is the way we print a color. When we compare RGB and CMYK, which we'll need to do to remember that relationship about how cyan blocks the red, we're fortunate because in most English-speaking parts of the world, we talk about RGB color for the additive color space of the scanner or the camera or the computer monitor, and we talk about print color often as CMYK. The K is black, and that's not part of our discussion today. But what you can see is that the order makes it easy for us. CMY is to RGB, so that cyan is the color that blocks red, magenta the color that blocks green, and yellow the color that blocks blue. I can also look at this on a color wheel, and if I make one of these triangles the additive colors, such as RGB, you'll see that I've now drawn in opposite each of those additive components the subtractive color, which is what we call CMY, that blocks that color. So opposite red is cyan, opposite magenta is green, and opposite blue is yellow. Now we're ready to understand what is a saturated color. A saturated color is often something that we could say is a strong color, but that's not a very useful description. We'd be more precise to say it's a pure color, but that doesn't quite help us all the way with our understanding either. The easiest way to understand saturated colors, which again are these very bright, pure colors that we see around the edge of the color wheel here, is that a saturated color can be described in terms of its wanted and unwanted components. Talking about the red example that we've mentioned a few times, since cyan blocks red, cyan is unwanted in a red, magenta and yellow are wanted. So here's a red color of a certain amount of saturation. Notice that as I move towards the edge of the color wheel, the red becomes more saturated. This makes sense, right? Since the less cyan in the red, the more pure the color is, and therefore the more chromatic it is, the more colorful it is. So I can look to see what colors make up the red color, and I can see that magenta and yellow, which are essentially right next to it on the color wheel, are the wanted components. The cyan down here, obviously, that made it dirtier when there was more cyan in it, is the unwanted component. Let's look at one more example. Let's talk about a saturated green. A saturated green in the lower right of this slide is very pure because it's very low in magenta. See how magenta is opposite the green? Magenta is the unwanted component in a green. Cyan and yellow are wanted. So if you asked me the definition of a saturated green, I'd say, well, all saturated colors are high in wanted and low in unwanted components. And if you said yes, but what about the green? I'd say the green is high in cyan and yellow, its wanted components, and relatively low in magenta, its unwanted component. the same as the red we looked at on the last slide. So here's the color wheel view of this. Red, if we talk about red, the wanted components are next to it. The unwanted is that cyan down at the bottom. You see that the wanted components sort of surround the red there. They are what makes up the red. If we look at a green, the magenta is unwanted. What are the wanted colors? They're the yellow and the cyan that surround the green. Is this starting to make sense? Okay, now we're ready to talk about tone curves. A tone curve is a way that we can adjust tonality or contrast of a digital file. A classic tone curve, like the one I'm showing you here, has the input along the bottom or the x-axis. Historically, this might be a photograph. Today, it might be a digital camera file, or if we've already separated our data into CMYK, these might already be CMYK dot values in Photoshop across the x bottom axis. The vertical y-axis represents %dot. %dot, remember, is how we print in the printing industry. We convert continuous tone photographs into halftones, which are tiny, tiny dots that hopefully your eye can't see, but we simulate tonality, that is the range of the tonal scale from light to dark, by using progressively larger halftone dots. Remember, this is because on a typical printing device, if we just consider black and white device for a minute, I don't have a white ink and a gray ink and a darker gray ink and a black ink. I normally just have a black colorant, ink or toner. If I want to show you a light gray area, I'll use tiny little halftone dots that are very infrequent. And if I want to show you a darker still area, I'll make the halftone dots either larger or I'll make them closer together to simulate more black tonality. So when we talk about printing dots, we talk specifically about %dot, as the scale shows here, which is really the % area coverage of those halftone dots. So at the very light end of the scale here, I have a highlight here, down here at the left side. That's typically where the lightest thing in the photo is mapped to the smallest dot I can print, maybe 3 to 5% area coverage. And on the other end, I have the shadow, which is the darkest point in the original scene, mapped to the largest dot I can print, or sometimes to the largest dot I can still resolve, which might be somewhere 95 or 97% area coverage. The other thing I want to talk about for a moment is why the tone curve typically has this convex shape. Most tone curves that you'll see on conventional repro systems always have this shape. They're not a straight line like the dashed line that I show here on this diagram. Why is that? The reason is because the range of the print, in terms of density, is much less than the range of the original photo. So in order to get contrast in the print, in the areas that your eye is sensitive, I need the curve to be relatively steep. That means the curve starts off steep at the left side here, where we're in the highlight, to the middle, where your eye is sensitive, and the curve becomes flat out in the darker areas, where your eye is less sensitive. Remember that where the tone curve is steep, the %dot is changing relatively quickly for small changes in the input, meaning we have high contrast, and where the tone curve is flat, we have relatively flat tonality, if you will, since the dots aren't changing very much even for large changes in the original. The reason I share this with you is once we go into a digital program like Photoshop or Image Viewer, we're typically going to see a linear transfer function like this. We're going to see a straight line. And the reason for that is simple. We've already done the color separation. We've already done what that tone curve accomplishes, which is called tone compression, has already occurred. So now we just want to map the input to the output, maybe in some different way to correct for some tonal problem in our print or our reproduction. Before we do that, I'll give you a little more language around the tone curve. Remember that the lightest area in the original is mapped to the smallest printing dot I can print. We call that the highlight. The dark area of the original, or the darkest point typically of the original, is mapped to the largest printing dot. We call that the shadow. In the middle, we call it the midtone, halfway between highlight and shadow. We have two more control points, one halfway between the highlight and midtone, called the quarter tone, and the last halfway between the midtone and the shadow called the three-quarter tone. So very often you'll hear discussion about this, and this is how people talk about tone adjustments. If I look at a digital imaging tone curve, I typically have this starting point that's linear, as I said, and I'm showing these control points on this curve just to make it easy for you to understand. What I want to get to now is if I make a tonal adjustment, how does that affect the colors in my print? And the answer lies in understanding the relationship between wanted and unwanted colors. Let's look at this tone correction. I lightened the quarter tone. Probably I looked at the print, or my customer looked at the print, compared it to some original or to some expectation they had, and they said, I think it's too dark in this light area here, in this picture of this person in this light gray shirt or this white shirt. That shirt looks too dark to me. It should be lighter. Let's lighten the quarter tone. This is the perfect way to adjust color, is always to adjust the tonality first. The reason is that this tone adjustment that I made to the quarter tone actually affected my colors as well. Why did a change to the quarter tone affect the colors? The answer lies in the fact that we need to think about this tone curve as a curve for cyan on top of a curve for magenta on top of a curve for yellow. When we move that tone curve, we move all the colors together. You know, if we go to our curves in Photoshop, we can also move, say, just the magenta curve or just the yellow curve. But that's not what we do with the tone correction. We move all the colors together. Now let's think about a saturated color. Let's take our example about a saturated red. A saturated red is defined as a color that has a certain ratio of wanted to unwanted components. Specifically, it is high in wanted components and low in unwanted components. So for red, where are the wanted components on the curve? And I'll remind you so you don't have to go back. The wanted components in a red are magenta and yellow. Well, magenta is an easy guess. Magenta is probably at 100% in red color. So if I draw magenta onto this tone curve at the right, remembering that the percent dot on the left Y scale goes from 0 at the bottom to 100 at the top, magenta is sitting up here. What about the yellow, the other wanted component in a red? Probably in the range of 80% in a bright red color. The yellow is also far up the tone scale. Where is the unwanted components on the tone curve? The unwanted component, in this case the cyan and the red, is right at the quarter tone. So even though my tone curve moved cyan, magenta, and yellow together, in a red color, the only thing it affected was the cyan that was sitting at the quarter tone, not the magenta and yellow that are way up near the shadow. What happened to that red when I took cyan out of it? Remember the color wheel? If we move towards the edge of the color wheel, away from the unwanted component, we get more saturated. So the answer is that by making this tone correction, I actually fixed the saturation of my red colors that hopefully I hadn't even looked at yet, or hadn't thought about because I knew that I wanted to adjust tonality first. In the case of a green, we see the same thing. Wanted components, cyan and yellow, are near the shadow. The unwanted, magenta, is near the quarter tone. With the same tone adjustment that I made to fix somebody's shirt, I took magenta out of greens and I increased the saturation of the greens as well. This is true for blue colors as well. Since the yellow is in the quarter tone, the wanted components are high. And this is true for a whole range of more complicated colors that I'm not going to talk about today. Any saturated color that is high in wanted and low in unwanted components is going to have its unwanted components moved and its wanted components not adjusted by this particular tone correction. So this is the explanation, the example that I wanted to give you today about how tone correction can actually naturally correct color without even having to think about it or make a mask or use some sophisticated tools. Before we close, I want to give you a challenge question. What if I darken the quarter tone? And now I'm in the full Photoshop tone curve here. If I darken the quarter tone, do you think the colors will increase or decrease in saturation? The answer is by moving up the quarter tone, I am increasing the unwanted component in all my saturated colors. I'm not moving the wanted components since they're up near the shadow where I didn't move the curve, and therefore this tonal correction will desaturate my colors, which before you get worried about that might be exactly the thing I need to do. If you find a reproduction where the quarter tone is blown out or is too light, chances are the color is unnatural looking too. It's oversaturated. By adjusting that quarter tone a little darker, back to its natural tonal placement within the original scene or photograph, you'll actually fix all your saturated colors in that same adjustment. So, I hope this has been helpful to you today. A quick review, we talked about how RGB color works and how it reminds us the light around us in the real world, the white light, is roughly equal in red and green and blue since that's what our eye measures. We talked about CMY color. These are the printing or photographic emulsion colors that selectively filter out red, green, and blue, so that if we want to print a red, we use a lot of magenta and yellow to block the green and the blue components, and only a little cyan since that blocks the red portion of the visible spectrum of the RGB. We talked about saturated colors and the definition that a saturated color is high in wanted and low in unwanted components. And that led us to understand that when we adjust tone curves, especially when we move just one end of the scale like the quarter tone or the three-quarter tone, we are naturally going to affect saturation because we're going to change the ratio of wanted to unwanted components in that saturated color. So that's the answer to why tone affects color. To learn more, please watch the World of Fiery webinar series available at this link. Several of these webinars are on color topics, as well as other digital imaging topics that might be interesting for you to learn more about. Thank you.